In section 4.4, we're going to study something called the fundamental theorem of calculus, and maybe as the title suggests, it is a very important theorem. Without exaggerating, we pretty much are going to use this theorem in every lesson from here on out, so definitely mastering it sooner than later is going to be a goal for all of us. So the great thing about this fundamental theorem of calculus, while we will be using it pretty much exclusively from here on out, it is a very basic theorem in terms of the way we use it. So first thing we gotta kind of realize back from 4.3 is that undoing a derivative or finding an antiderivative gave us the ability to find the area under a curve. We saw that back in 4.3, how these two seemingly unrelated topics of areas under curves and antiderivatives are related to each other. So we wrote out a definite integral back in 4.3. When you saw these bounds of a and b on an integral, that was indicating to you to find the exact area from a to b under the curve of f of x. But we didn't have a way to figure that out. If we didn't have bounds on this integral, we could have done this problem like we did back in 4.1 when it was an indefinite integral. But this fundamental theorem of calculus will give us the ability to evaluate these definite integrals. So how do we take this and evaluate it? Well, the fundamental theorem of calculus says we take the antiderivative and plug in b, we take the antiderivative and plug in a, and then we just subtract those two values. So that's really it. As long as you realize that big F is the antiderivative of little f, then what this fundamental theorem of calculus says is that we're going to plug in the top bound of b, plug in the lower bound of a, and subtract those two values. So let's go ahead and look at a very basic example here, one where we actually don't need this fundamental theorem of calculus, but I'm going to use it to kind of get us to the more complicated problems. So we want to find the area between the graph of f of x equals x and the x-axis on the interval of 0 to 3. And you can see geometrically, it's just a triangle with a base of 3 and height of 3. So we can of course find that area like we did back in 4.3 with just simple geometry. And you can see here that's 9 over 2. But now that we know this fundamental theorem of calculus, let's see if we can use it to verify that the area is 9/2. So first thing we need to do is set this integral up. We're trying to find the area, which I hope you equate to taking an integral. We want to find the area under the curve of x from 0 to 3. So the first thing we have to do is set up this integral. Once we have that set up, we know that the integral of x is x squared over 2, and then we can't forget that plus c. The next thing we're going to do notationally is draw a bar, this vertical line, and put that lower bound of 0 and that upper bound of 3 next to that bar. What that bar is telling us to do is to evaluate the expression first at 3 and then at 0 and subtract those two values. So again, once we started this chapter 4, we were introduced to a bunch of new notation, and here's one more last bit of notation that you're going to need. So let's go ahead and do that. Let's plug in that upper bound of 3. 3 squared is 9, so we're going to get 9/2 plus c. And then we're going to take the lower bound, which is 0, plug that in. 0 squared 0 divided by 2 plus c. And then again, we're going to subtract those two values. And you'll notice something. Those c terms will cancel. If you take c and that other c and subtract them away, they're going to cancel. And this is the first and the last time you'll ever see me put a plus c on a definite integral. The good news is you don't need to put the plus c ever again as long as you're dealing with a definite integral. In other words, there's an upper and a lower bound. Of course though, if there are no bounds on this integral, you would still have to put that plus c to represent that general solution. Okay, once you kind of have that idea mastered, it's just a matter of doing the arithmetic here to figure out the answer. 9/2 minus 0 is just 9/2, but again, we kind of already knew that from us using the algebra from before. Okay, let's take a look at another example, and unlike the last example, this one we can't use geometry to figure out since we're dealing with a curve x squared. And we want to find the area under x squared and above the x-axis from 0 to 1. So the very first thing we need to do is set up an integral that represents that area. That's the concept that we figured out back in 4.3. The new thing in 4.4 is now we have the ability to figure out this integral using the fundamental theorem of calculus. And just as a little reminder, I've added this little rectangle here just again to represent that we're adding up an infinite amount of rectangles. The height of these rectangles are represented by the function x squared, and the base of these rectangles is a little change of x, or dx. So just a visual reminder of what we're doing conceptually here. But now for the process. How do we integrate x squared? Well, we're just going to use the power rule that we know. We add 1 to the power and we divide by that new power. So we get x cubed over 3, and where normally we would put a plus c after that, we're not going to do that anymore because you saw in that last slide, those c's would always cancel out. So we're going to take the upper bound, plug it in, take the lower bound, plug it in, and subtract those two values. That's what the fundamental theorem of calculus tells us to do in terms of evaluating these definite integrals. Of course, that second term will just give us a 0, so it turns out the area from 0 to 1 is 1/3. In this trig example, we're trying to find the area under the sine curve from 0 to pi. And again, just as a visual of what's going on conceptually here, that rectangle is representing one of an infinite amount of rectangles, where the height of those rectangles is the function sine x, and the base of those rectangles is a little change of x, or dx. So we have to set up our definite integral to find this exact area. To find the area, we're going to integrate our function sine x with respect to x from 0 to pi. The integral of sine x is negative cosine x, and then we have to be good with our notation here and put that bar from 0 to pi. Using the fundamental theorem of calculus, we're going to take the upper bound of pi and plug it in, take the lower bound of 0 and plug it in, and when we evaluate both of those and subtract them, we'll get a value of 2. In another trig example here, we're now finding the area, or being asked to find the area, underneath the cosine curve and above the x-axis, from pi over 4 to pi over 2. So the first thing we have to do is set up an integral that represents that area. We're trying to find the area under the cosine function with respect to x, so we're going to integrate cosine x dx. And we want to find that area from pi over 4 to pi over 2. The integral of cosine is sine, and then we're going to put the bar with no plus c from pi over 4 to pi over 2. We're going to take the top bound of pi over 2, plug it in first. We're going to take the bottom bound, or the lower bound of pi over 4, plug that in next, and subtract those two values. Sine of pi over 2 is 1. Sine of pi over 4 is square root of 2 over 2. And I guess we could leave the answer as that, but I'm going to go ahead and combine those two to be one fraction, which will give us 2 minus the square root of 2 over 2. In this last example, we're not starting off with a picture here, we're just being asked to evaluate the integral from 0 to 1 of the square root of 1 minus x squared dx. The first thing I hope you can appreciate real quick here is we can't actually figure out this integral. Based on what you guys have learned up until now, we don't know how to do this integral. And don't make a mistake here. You might want to write this off in the margins and not on the actual notes here. But the square root is not equal to 1 minus x. In other words, we can't take the square root of the 1 and then take the square root of the x squared separately. Since they are terms under a square root, we're not allowed to do that. So unfortunately, we're kind of stuck here. We can't simplify this to just be integral friendly, which is a number in x and a power. So we're kind of stuck here. Unless you realize something about this particular function, the square root of 1 minus x squared, we can actually solve this problem with geometry like you saw back in 4.3. I guess you're going to have to be up to speed though on your conic sections. So this is what we call a geometric integral. We're going to use geometry instead. And to help you see that this equation here is something that we know the picture of, I'm going to go ahead and set y equal to the square root of 1 minus x squared. And then I'm going to square both sides and then move over that x squared. By doing that, maybe you recognize this as the equation for the area of a circle, where that number at the end, which is r squared, is our radius. So it turns out that we just have a circle of radius 1 here. And if we're trying to find this integral, which is telling us to find the area from 0 to 1, we're just really trying to find the area of a quarter of this circle. So the area of a circle is of course pi r squared, and we're going to divide that by 4. Since we now know that the radius of this circle is 1, we're just going to take that 1, plug it in, and simply get a value of pi over 4. Okay, moving on with a few more examples. We want to find the area under the function that is above the x-axis. So the first thing you might be realizing compared to the first set of examples we did is we don't have any bounds that are given. They're not telling us from where to where we're trying to find the area. What we need to do is, since this is an upside down parabola because of that negative symbol in front of the x squared, we need to find where this graph crosses the x-axis. So to find that, we're just asking to find our x-intercepts. And of course, find x-intercepts, we need to take our equation, set it equal to 0, and we're going to find that we have two x-intercepts, x equals 2 and x equals 4. So now that we have a visual of what's going on, really we're asking ourselves, or we're being asked to find the area under our curve from 2 to 4. So this one just required that little extra step of finding those x-intercepts so we can figure out what area we're actually looking at here. Once we do that, now this problem is just like the ones we saw previously. We need to set up an integral that represents the area under this curve and above the x-axis. So that integral is going to go from 2 to 4, and we're going to integrate our function with respect to x. Since we have three separate things separated by pluses or minuses, we can integrate each of those individually. Negative x squared becomes negative x cubed over 3. 6x becomes 6x squared over 2, or just 3x squared. And then the integral of negative 8 is negative 8x, and again, no plus c. We're going to put the bar from 2 to 4. By the fundamental theorem of calculus that we learned in this lesson, we're going to take the upper bound of 4 and plug it in. We're going to take the lower bound of 2 and plug it in, and subtract those two values. When you do the math for plugging in 4, you'll get negative 16 over 3. When you do the math when you plugged in 2, you'll get negative 20 over 3. And when we combine those two things, we'll get an area of 4/3. Some problems like this one are kind of, I guess, neglecting the concept of finding area, because we're not going to deal with a picture in this problem here. All we're being asked to do is evaluate the integral, the definite integral, from 1 to 2 of 2x minus 1 over x cubed dx. But just don't forget that this is actually asking us to find area. While it's not being asked of us in this particular problem, that is just asking us to find the area from 1 to 2, even though it's really not going to play a part in this problem. So this is really more of a 4.1 problem in essence. How do we integrate 2x minus 1 over x cubed? Well, the first thing we need to realize is that's not written in what I call integral friendly. It's not a number, an x, and then a power. So the first thing we should do, and we've seen this many times with problems, is to split this fraction into two pieces. Since we have terms in the top and one term in the bottom, we can split that into two separate fractions. Since we have 1x in the top of the first fraction and 3x's in the bottom, we can cancel one of those out. So 2x over x cubed just becomes 2 over x squared. We're almost ready to make it integral friendly. We just need to take the x squared in the bottom of the first fraction and the x cubed in the bottom of the second fraction and move those to the top as negative powers. So we're really trying to integrate the function 2x to the negative 2 minus x to the negative 3. Once we have it written that way, which is integral friendly, we can integrate each of those separately. To integrate each of those separately, we're going to use the power rule, which means we're going to add 1 to the power and divide by that new power. 2x to the negative 2 becomes 2x to the negative 1 over negative 1, or just simply put, negative 2x to the negative 1. When we take x to the negative 3 and add 1 to the power and divide, we'll end up with 1/2 x to the negative 2. Of course, we're trying to evaluate this without a calculator, so we should really take a step to rewrite this a little more simplified. That x to the negative 1 power we can send to the bottom of that fraction, and that x to the negative 2 we can send to the bottom of that fraction as well. Once we have our antiderivative simplified, now we can apply the fundamental theorem of calculus, where we take the upper bound of 2 and plug it in, and we take the lower bound of 1 and plug it in, and then subtract those two values. When you evaluate the function plugged in with 2, you'll get negative 7/8. And when you evaluate the function evaluated at 1, you'll get negative 3/2. And when you combine those two values, you'll get 5/8. One application of the fundamental theorem of calculus will lead us to this little concept called the average value of a function. And using this picture here, you're going to have to start off, before we talk about average value, realizing that the area of this rectangle that you see from A to B and the area under the curve f from A to B have the same value. They are equal to each other. This area for the rectangle, which has the width from A to B and the height of f of c, and then the area under the function f from A to B, those two areas are equal to each other. And when we're talking about average value, we're talking about the height of the rectangle that would have the same area as the area under a curve. And to find that value, it's just the integral from A to B of f of x dx, which finds the area under the curve, and then you're going to have to multiply that by 1 over the difference of b and a. So let's go ahead and try to apply this little formula here and find the average value of this function from 1 to 4, and also where it obtains that average value. So just as a little visual, we're dealing with the function 3x squared minus 2x from 1 to 4, and I want to find the height of a rectangle that would have the same area as the area under the curve. So to do that, we need to find the average value here. To set this up, we just need to set up an integral, and in front of that integral, put a fraction. And in this case, our a and our b are 1 and 4, so a is 1, b is 4. We'll plug those values in, and that's it. Setting it up is nice and simple, and to move on from here, we just need to integrate this function. So the integral of 3x squared would be 3x to the 3 over 3, or simplified, x cubed. The integral of 2x would be 2x squared over 2, or simplified would just be x squared. Of course, that 1 over 4 minus 1 just becomes 1/3 in the front. And now the new thing we learned in this lesson is that to evaluate this integral from 1 to 4, we're going to apply the fundamental theorem of calculus. So we're not going to put a plus c here. We're just going to put the bar notation and then put the lower bound of 1 and the upper bound of 4. The fundamental theorem of calculus tells us to plug in the upper bound first, which is 4, so we'll get 64 minus 16. We'll plug in the lower bound next, which will just be 1 minus 1, and then we subtract those two values. 64 minus 16 is 48, and of course 1 minus 1 is just 0. We don't have to worry about that. 48 divided by 3 is 16. So that's the average value, or in other words, it's the height of a rectangle that would have the same area as the area under the curve. To find the x value that happens at, or the c if you use the picture from 4, we're just going to take our function and set it equal to that y value. If we're trying to find the x value that our function is 16 at, then of course we're just going to plug in 16 for y. Since this is a quadratic equation, we need to move everything to one side to keep it equal to 0, and then we can factor that expression. When you solve both of those factors equal to 0, you'll get two values, 8/3 and -2. One of these values doesn't apply, and I think you can see real quick that -2 doesn't apply because it's not in our interval. It's not in the window of 1 to 4. So the x value that the rectangle has a height of 16 at is at 8/3. And now visually you can see if I draw that rectangle in, the area of that rectangle and the area under the curve from 1 to 4 have the same area. Okay, here's a great AP test practice problem that's going to hopefully get you to see something you might have realized back in 4.3 when we were finding these areas visually or geometrically, and that is this. An integral function is what we call an accumulation function or an area so far function. The reason it's called that is because as we move from left to right, we're adding up all these areas to figure out the net area. Area above the x-axis is positive, area below the x-axis is negative. So here we're going to define a function g to be the integral from 0 to x of f of t dt, and we have the graph of f below here. In part A, we want to find g of 0. G of 0 is just asking us to plug in 0 for x. And if we plug in 0 for x, we'll get the integral from 0 to 0 of f of t dt. We actually don't even need the picture here to figure out this integral, because this integral is asking us to find the area from 0 to 0. And if we have nothing to look at, since it's from 0 to the same point 0, we know that area must be equal to 0. In part B, we need to find g of 2, which means we need to plug 2 in for x, which gives us the integral from 0 to 2 of f of t dt. That's asking us to find the area between the curve and the x-axis from 0 to 2. And you'll notice the shape we have there is, or I'm going to split the shape that we have there into two shapes, a triangle and a rectangle. To find the area of the rectangle, we'll do 2 times 1. To find the area of the triangle, we'll do 2 times 2 divided by 2, and we get an area of 4. In part C, we want to find g of 5, or in other words, plug in 5 for x, which gives us the integral from 0 to 5 of f of t dt. So going back to the top here, we need to realize that an integral function is an accumulation function or an area so far function. We know that the area from 0 to 5 can be found by taking the area from 0 to 2 and adding to it the area from 2 to 5. The area from 2 to 5 is a quarter circle, and we know that the area from 0 to 2 is what we found before to be 4. That quarter circle has a radius of 3, so since it's a quarter of that circle, we'll multiply by 1/4. When we simplify that, we'll get 4 plus 9 pi over 4, and there's no need to simplify any further after that. In part D, we want to find g of 9. Which is telling us to plug in 9 for x, which will give us the integral from 0 to 9 of f of t dt. To find the area from 0 to 9 between the function f and the x-axis, we'll take the area we just found from 0 to 5 and add to that the area from 5 to 9. That area is below the x-axis, so it's going to be a negative value. And on top of that, it's also another quarter circle. So I'll go ahead and label that here as a quarter circle again, so you can see that. Okay, so the area from 0 to 5 turned out to be 4 plus 9 pi over 4, and then we're going to add to that the area from 5 to 9, which is again the quarter circle. That quarter circle is below the x-axis, so it's going to have to be negative. When we do the math here, we'll get 16 pi over 4, and since both of these fractions have a common denominator of 4, we can combine them easily and get 4 minus 7 pi over 4. In part E, we want to find g of 11, which means to plug in 11 for x. That gives us the integral from 0 to 11 of f of t dt, which is asking us to find the area from 0 to 11 between the function f and the x-axis. We just discovered that the area from 0 to 9 was 4 minus 7 pi over 4, so now we just need to take the area from 9 to 11, which is a triangle, and add to that the area from 0 to 9. The one thing we have to keep in mind here is that since that area is below the x-axis, it has to be negative. And just to label the shape here again, that area, or that shape, is a triangle. So since it's below the x-axis, it'll be negative 2 times 4 over 2. When we simplify, we'll get a negative 4, and luckily that cancels with the 4 in the front, and it can simplify to be simply negative 7 pi over 4. In the last example here, we're being asked to find g of negative 1, which is telling us to plug in negative 1 for x. And you might be noticing something about this, or I hope you're noticing something about this, in that it doesn't seem like it's written correctly. And if that doesn't seem like it's written correctly to you, then you should realize that it is okay to switch the bounds. The reason we want to switch the bounds is because the lower bound needs to be the smaller number, and the upper bound needs to be the bigger number. If you switch those bounds, you need to recall from 4.3, we need to put a negative in front of that integral. I'm going to go ahead and wipe out all the shapes I drew on the picture here, and just focus here from negative 1 to 0. The shape from negative 1 to 0 is just this little triangle here, and it's above the x-axis, so it's positive. But that negative in front is from the switching of our bounds. When we do the math here, we'll find that that area from negative 1 to 0 is negative 1/2. Okay, in this AP test practice problem, which is a free response problem, we're going to use the fundamental theorem of calculus in a little bit different manner than we have in the previous examples. So we have a graph here of a differentiable function f from negative 3 to 3. Our graph f has horizontal tangents at negative 1, 1, and 2. The area of region A, B, C, and D is 5, 4, 5, and 3, respectively. We're going to let g be the antiderivative of f, such that g of 3 is equal to 7, and we want to find the value of g of 0. So in an ideal world, we would have been given the function g so that we could plug 0 in. Unfortunately, we don't have that. The one thing we have here that is very, very important is that they tell us that g is the antiderivative of f. Or in other words, if I were to integrate the function f with respect to x, I would get the function g plus c. So how are we going to use that to figure out this problem? Well, normally what we would have done is if we knew what the function f was, and then we found our function g, we would have used this point that they gave us to find the value of c, and then we would have had our g function, which then would have led us to plugging in 0. Unfortunately here, we don't know what the function is, so we can't integrate it. We just know that the integral of f gives us g. So the only thing we have left to do as an alternate method is to use the fundamental theorem of calculus as a formula, so to speak, since we don't have that function to actually find the antiderivative of. So what do I mean by using the fundamental theorem as a formula? Well, we know that if we integrate a function f from a to b, its antiderivative, which in this case is g, would need to be evaluated at the upper bound and then at the lower bound and subtract those two values. So that's what we're going to have to do in this case. To find g of 0, we're going to have to approach the fundamental theorem as a formula. And you'll notice it just is 3 pieces that we're looking to find. The left of the equation, and then the 2 values to the right of the equation. So I guess the question would be this: what would be the bounds on our integral in this problem? Well, if you read between the lines a little bit, so to speak, you'll realize that since we're trying to find g of 0, and since they give us g of 3, those would need to be our bounds. Because when we integrate f, we're going to get g. And since we're using the fundamental theorem of calculus here, since our integral has bounds, that would be equal to g of the upper bound, which is 3, minus g of the lower bound, which is 0. How does this graph play a part? Well, this integral from 0 to 3 of f of x dx is really just another way of saying find the area from 0 to 3 between the curve and the x-axis. If you think about what was stated in the problem, we know the area of A, B, C, and D are 5, 4, 5, and 3 respectively. We also know g of 3 is equal to 7. So if we put this information together, we can just plug in the two values we know so that we can find the value of g of 0. The area from 0 to 3 would be 5 plus 3. It'd be the areas C and D. So that would be 8. We know g of 3 is 7, and we're looking for g of 0. If we subtract 7 and then multiply by that negative in front of g of 0, we'll find that the value for g of 0 is equal to negative 1. So again, keep in mind, I guess in a different scenario, what we would have done is found the value of c after we integrated so that we could plug in 0 for g, or to find the value of g of 0 by plugging in 0. But in this case, we didn't have an equation or a function to take the integral of, so we had to use this alternate method by using the fundamental theorem of calculus as a formula. Okay, another great AP test practice problem. Here we're given water that's being pumped into a tank at a rate given by that equation. So as soon as we see that that's a rate, that must be a derivative. T is in minutes since the pump was turned on. They also tell us that the tank contained 800 gallons of water to begin with. So the volume at time 0, so V of 0, is equal to 800. We want to figure out how much water is in the tank after 20 minutes. So we want to find V of 20, and we don't know what that's equal to. So how are we going to do this problem? Well, here we're not going to integrate the function. We don't know how to integrate this function. If you think about it, we haven't looked at integrals of e's to powers and stuff like that. We don't know how to integrate this function. And even more so here, a calculator is allowed. So we would be kind of doing more work if we did it by hand anyways. So kind of look at that from those 2 points of views. We're going to use the fundamental theorem of calculus here, like that last example, as a formula because A, we don't know how to integrate the function, and because a calculator is allowed in this problem. So if we integrate our function r from t1 to t2, we know by the fundamental theorem of calculus that that would be equal to the volume at t2 minus the volume at t1. The integral of this rate gives us volume. And because we're using the fundamental theorem of calculus, we need to plug in the upper bound, which is t2, and then subtract away the value when we plug in the lower bound of t1. So in this problem, again, like the last problem, we have to kind of read between the lines to figure out the bounds here, but they give us v of 0, and we want to know v of 20, so of course 0 and 20 must be the bounds. When we apply that to the fundamental theorem of calculus, that integral is equal to v of 20 minus v of 0. And to find the integral from 0 to 20 of r of t dt, we're just going to use the TI-89. Back in the previous example, we had a picture or a graph that told us the area that we were trying to find. In this problem, we're given an equation and not a picture, so we can use our calculator to figure out this integral. And that would be a great time to pause here and try to type this in your calculator and make sure you can get 420.143. So the way we type this into the calculator is we're going to go to F3, which is calc, and we're going to choose the integral. That's going to put this little integral symbol right here on our line that we type stuff on. And then the format we need to follow, you can see below. We're going to put the function, comma x, comma the a, which is the lower bound, comma the b, which is the upper bound, and then close those parentheses. That's the format that you have to type into the calculator to get it to give you a definite integral. If you are interested in other problems to find an antiderivative, just note that if you want to find an antiderivative, all you need to do is leave off the lower and the upper bounds, and then close the parentheses after the x, if you ever need to know what an antiderivative would be equal to. If again all goes well, you'll get 420.143. We know v of 0 is 800. The volume at time 0 is 800. So we can plug in the 800, and when we add that to the other side of the equation, we'll find that the volume after 20 minutes is 1,220.143 gallons. Okay, just to make sure we didn't lose a very, very important concept as we've been talking about 4.3 and 4.4. If you ever see this thing, which is called a definite integral, you know that that's another way of saying area. That's asking you to find the area between the function and the x-axis from a to b. So something that we need to kind of formalize here, because we're going to move on to something called the second fundamental theorem of calculus, is those bounds were always constant. It was like the area from 0 to 1, or 2 to 3, or whatever the case might be. When those values were constants, we found an area which is also a constant value. It didn't have x's in it or any variables, and that's what we were used to getting up until this point. But what if we have an integral where the lower bound is a constant, but the upper bound is a variable? We can actually still do that integral, but the answer we would be getting is a function in terms of that variable x. It wouldn't be a single number like we'd get over here where it was just an area. We would actually get a function in this case, and that function would be in terms of the variable x. The reason we need to go over that is because we're going to see problems like this that appear below. Here we're being asked to do something kind of interesting. We're asked to take a derivative. This right here is asking you to take a derivative of an integral. So how are we going to do that? Well, I'm not going to talk about that second fundamental theorem of calculus yet. That's kind of a shortcut to doing this problem. Let's do this problem the long way first, and then let's see what this second fundamental theorem of calculus lets us do in terms of a shortcut. So forget about the derivative for now. We're not going to take the derivative yet. I'm just going to focus on taking the integral on the inside of those brackets. The integral of cosine is sine. We're going to put the bar from negative pi to x. Again, we're forgetting about taking a derivative right now. We're going to take the upper bound, plug it in. We're going to take the lower bound and plug it in. So we'll end up with sine x minus sine of negative pi. Sine of negative pi is 0, so we're just left with sine x. And now we can apply the derivative. We did the parentheses first. This is still using PEMDAS, so we had to do what was inside the parentheses first, and now we can apply this outside instruction. And the outside instruction is telling us to take the derivative of that inside thing. Here it's sine x, so the derivative of sine is cosine. So I called that the long way. It really wasn't that long, but maybe in other problems the long way might be really long. There is a shortcut to doing problems where you need to take the derivative of an integral, especially if that integral has an upper bound that is a variable of some sort, as you can see right here and in the problem I did right there. If you are asked to take the derivative of an integral from a to some function that I'm going to call g, it turns out the answer is as easy as taking g, plugging it into f of x, and then multiplying by the derivative of g. So what I did here is I translated this formula that you can see in books and online, and hopefully now it'll make a little more sense. All you need to do, and you're going to see this little pink arrow appear here, all you need to do is take this function g and plug it into your function f, and then multiply by the derivative of that function g. So let's see if we can apply that shortcut to doing that same problem we just did before. So it's just 2 steps. We need to plug in the upper bound, which in this case is x. So of course that just becomes cosine x. And then we need to multiply by the derivative of that upper bound that we plugged in. And the reason we have this g prime here, or the reason we need to multiply by the derivative of that bound, is because of the chain rule. We're always thinking about using the chain rule when we're taking derivatives. Of course, the derivative of x is just 1, so 1 times cosine is just cosine x. So you can see, whether it was the long way or using the shortcut, which is called the second fundamental theorem of calculus, we still got the same answer. It's just in other problems, maybe the long way really is a lot longer than using the shortcut. Okay, in this last example, I hope to illustrate how the second fundamental theorem of calculus is definitely a shortcut for doing these problems the long way. So, how do we know that this is an application of using the second fundamental theorem of calculus? The first thing we can realize here is that we're being asked to take the derivative of an integral. And on top of that, the integral has an upper bound that is a function. When we kind of realize those all to be true, we know that we can apply the second fundamental theorem of calculus. But like I said at the beginning, we're going to do this one the long way, just to kind of appreciate why using the second fundamental theorem is definitely a much quicker, direct path to the answer. So we're going to forget about the derivative in the front of these brackets here and just focus on the inside, and that is to take that integral. The integral of t squared would be t cubed over 3, or written a little more simpler maybe, 1/3 t cubed. The integral of 3t would be 3t squared over 2, but I'm going to write that as 3/2 t squared. Instead of putting a plus c, we're going to put a bar, and then put our bounds of x squared and 1, because this is a definite integral. The next step is to apply the fundamental theorem of calculus. And the fundamental theorem of calculus states that we have to take the upper bound and plug it into our antiderivative. And then we take the lower bound and plug it in to our antiderivative. And then we subtract those two values. So a subtraction separates when we plug in the upper bound and when we plug in the lower bound. Okay, so we can definitely try to take the derivative of this as is, but I think it's probably a good idea to simplify this expression first. When we have a power to a power, we multiply those two numbers. So to simplify this, we'll end up with 1/3 x to the 6th plus 3/2 x to the 4th. And then this negative we can distribute to both of these terms. So we'll end up with minus 1/3 minus 3/2. Now that we've simplified the inside of our brackets there, now we can apply this derivative. We can take the derivative of each of these pieces individually. The derivative of 1/3 x to the 6th will bring the power down, which would be 6 over 3, and that's 2. Reduce the power by 1, which is x to the 5th. When we bring the power down to 4, 4 times 3 over 2 is 6. We'll reduce the power by 1, which gives us x cubed. And just be careful, the derivative of this negative 1/3 and this negative 3/2, since those are constants, would be 0. And of course, we can just leave off those zeros for a final answer of 2x to the 5th plus 6x cubed. Okay, so instead of doing it the long way, if we realize that we can apply the second fundamental theorem of calculus, we of course, what I hope, would want to take that shortcut. And it's just 2 steps you have to do. The first step is to take that upper bound, your function, and plug it in to your expression on the inside of the integral. So here we're going to have x squared to the 2, and then we're going to have 3 times x squared. And then by the chain rule, since we're taking a derivative here, we need to multiply by the derivative of that upper bound that we plugged in. And again, in this case, it was x squared. After that, it's just a matter of simplifying. Again, when we have a power to a power like we have here, we multiply. So x to the 4th plus 3x squared, and then the derivative of x squared is nice and easy, and that's 2x. Only one more step to go, and that is just to take our 2x and distribute it to both of our terms on the inside, and sure enough, it turns out to be the same exact answer. So definitely use the fundamental theorem of calculus when it's appropriate.